Hi students, welcome to Science Extension and Module 1, the Foundations of Scientific Thinking. This is video number 9 and we're going to be looking at paradigm shifts. The specific learning intention for this video is for you to select one example from the following list to analyse the paradigm shift and how evidence is used to support new theories to explain phenomena and their consequences. And the 4 examples you have to choose from are Lavoisier and Oxygen, Einstein and general relativity, Wagner and continental drift leading to plate tectonics, or McClintock and transposable elements, also known as jumping genes. Lavoisier and Oxygen. In 1777, Lavoisier published some papers around the oxygen theory of combustion. Now, it wasn't really the discovery of oxygen. We kind of had a bit of an idea about oxygen before then, but we had this theory of a German's style around phlogiston. So phlogiston was the theory that things that were burned or during combustion reactions, there was this kind of fire release of this substance called phlogiston. And that all things that were being burnt, that was a characteristic that was common about all of them. For example, charcoal, when you burned it, lost weight. And that was a result of the phlogiston component mixing with the atmosphere. But as further experiments were conducted, particularly those by Joseph Priestley, we found that certain metals, when they were combusted, increased their weight. So were they taking in phlogiston? That didn't seem to quite fit the theory. Priestley carried out some experiments, collected the gases released by heating metallic oxides, particularly things like mercuric oxide, and he found that the gases that he collected enhanced respiration and allowed candles and things to burn for longer periods of time. But it was Lavoisier who looked very specifically at combustion reactions and labeled combustion reactions as the reaction of a metal or an organic substance with a particular part of the common air. He did that through the combustion of mercury using this kind of swan-necked flask arrangement that you can see on the slide. What happened was that as he carried out this experiment, not only was he able to identify the presence of this particular gas that was involved in combining with the metal in order to undertake that oxidation, that combustion reaction, but he also measured the proportion. He knew, for example, that about 1/5 of the air had been used in the reaction. He also knew that the component of air that was left was no good for respiration. So we now know that it would have been completely deprived of oxygen. You can see we also know that the air makes up about 20% of the oxygen. So the ratio of 1 to 4, and he basically had a word for the non-oxygen bit that linked to basically no life. So it was kind of an azone sort of name for the bit of the air that didn't contain oxygen, and he identified that the bit that does help life, that is involved in respiration, is oxygen. His theory was a keystone for the reformulation of chemistry. It's often described as the chemical revolution because this very important discovery and naming of oxygen, we know oxygen is just involved in so many important reactions in chemistry.